Well, welcome back to the first of our topics for the new year. Hopefully you've done some pre-reading on this and it will be a little bit straightforward, so let's get right to it. We're looking at chapter 7, okay, in case you haven't figured out where we are in our textbook, and we're looking at an introduction to equilibrium. The IBO statements for this are basically that you have to understand that equilibrium is reached in a closed system when rates of the forward and reverse reactions are equal, and you have to be able to define and describe the characteristics of chemical and physical systems in equilibrium. Okay, and these are the ones that we're going to look at the moment. In order to be able to do that, you really need to be able to define what an open or closed system is, understand that chemical reactions, even though we've told you chemical change is irreversible for the last 5 or 6 years, are actually reversible things, that most chemical reactions, or at least a large proportion of them, can go in either the forward or the reverse direction. You need to be able to define the conditions for equilibrium and explain what is meant by the term dynamic equilibrium, and then sketch graphs depicting these systems. And we'll look at these topics over the next 2 videos, this one and one more. Just in case you want a crash course hit, there is of course a link to the crash course Introduction to Equilibrium, which is pretty good. Again, it is pretty quickly and gives you an overview of the whole thing. So the first thing that we need to look at is defining an open versus a closed system. And this is fairly intuitive, but we need to know what can pass in or out of an open system or closed system, and what that means for what's going on inside in terms of our reactants and products that is present. We can only get equilibrium if we are looking at something like this one here in A, which is a closed system. Okay, so everything needs to be in the same vicinity. We can't have equilibrium being reached in an open system where the products are free to leave. Okay, so in an open system, the system can exchange matter and energy with the surroundings. So if you think about when you've reacted calcium carbonate, which is what this one is here, it's decomposition, or better still, reacting it with hydrochloric acid. So when you've put marble chips into hydrochloric acid, we know that we see effervescence. We see that bubbles of CO2 gas being produced, and that's the bubbles leaving the system. If we have the container open, it goes out into the atmosphere, and those products are lost to the direct system that we're talking about. Okay, whereas if we close this system, don't allow the gas to escape, those gas particles are still going to be present within the vessel that we're doing the reaction. So as the reaction occurs, we have reactant particles being present, we have product particles being present, and with according to particle theory and kinetic molecular theory, all of those particles will be able to collide with each other. So if the product particles are able to collide with sufficient energy in the correct orientation, there is nothing that says they won't react in order to form the reactants back that they came from. Okay, so that idea of particle theory that we looked at in energetics holds here too. All we need is the components of something to be able to collide with sufficient energy to overcome activation energy and the right orientation. So when the products are present for a reaction, okay, the calcium oxide and the CO2, they could collide with each other and cause the reaction to go back in the other direction. So let's look at the Haber process. This is the formation of ammonia from nitrogen and hydrogen. We've seen this reaction a lot. It's a good example for exothermic reactions, and it's a good example for us to look at equilibrium. Okay, so we understand that if we react 1 mole of nitrogen with 3 moles of hydrogen, we will produce 2 moles of ammonia. So this is what we would expect. We would expect that if we could react this in the correct ratios, that according to stoichiometry, we would always produce 2 moles of ammonia for every mole of nitrogen. However, this doesn't happen, okay? What seems to happen is the reaction seems to stop, we get a less than 100% yield, and there's not much that we can do to drive this reaction further. Okay, so if we just let it go, we never get those 2 moles of ammonia no matter how long we leave it. What's happening here is that ammonia, when it's heated, can actually decompose, and the decomposition reaction can occur rather than the synthesis reaction. So ammonia will form nitrogen and hydrogen. So under the conditions of the Haber process, where we're heating the hydrogen and nitrogen to meet that activation energy requirement and increase the rate, ammonia, as it's produced, some of it can actually decompose and go back to form the reactants, which means that we can never reach 100%, because if some of that ammonia is being decomposed, it won't be there when we work out our yield. This happens when we have equilibrium. So essentially when we're talking about here is that we're going in the forward reaction from reactants to products, but at the same time these products are reacting to go back and decompose and form the reactants. Okay? This will go on, and eventually if the system is closed, then what happens is the forward reaction and the reverse reaction are happening at the same rate. We are making product at the same rate of which we are breaking down product. And a good analogy for this is like if you're walking up an escalator the wrong way and you manage to maintain your speed at exactly the same as the escalators, you will be appearing to stand in place even though you are still moving. Okay? And this is where we need to start thinking about the fact that equilibrium is a dynamic process. That movement needs to keep going. If you stop, you'll just go down. You'll move in one direction. So there's always something going, because if the reverse reaction stopped here, then it would be the forward reaction that continued. And if the forward reaction stopped, then we would end up with the products. This is a constant cycle of backwards and forwards. So essentially what this means for industry is that we need to know the conditions under which we can get the maximum yield. Okay, industry is all about money. So if we have a reaction that reaches equilibrium before we have much product being made, it's not going to be really good. Okay, so when we talk about yield, what we're talking about is the percentage of the product that we get compared to the theoretical, our pure stoichiometry calculation. And we've seen yield before when we did stoichiometry. So essentially, if we have a low yield, we're going to have a large amount of unreacted starting materials lurking around. It's going to make it harder to purify. That would be a waste. It's going to make it costly for industry. So equilibrium is a really big consideration for industry and manufacture. So what industrial chemists do when you try and optimize a reaction for industry is to manipulate the position of equilibrium to try and make as much product as possible, and we will look at that in a later video. So as I said, all of this relies on the fact that we understand that reactions are reversible, because it requires us to realize that while we talk about reactants and products, the reactants can form the products, and when the products are formed, they are just simply reactants for the reverse reaction. Okay, so eventually the reactants and products are forming at the same rate, and this is when we have dynamic equilibrium. When we are talking about an equilibrium process, we must use the double-headed arrow, okay, which we've seen when we talked about weak acids and weak bases, where we talked about how the extent of the reaction wasn't 100%. Okay, now if we're talking about a system in equilibrium, or you see an equation that uses a double-headed arrow, it is at equilibrium. So if we look at what's happening to the formation reaction when we're talking about the formation of ammonia, we can plot these graphically in a couple of ways. If we look at the concentration over time, we can see that if we're going from the reactants A to B, the concentration of the reactants decreases as they're used up, which makes sense. And if we relate this back to our rate, that decrease in concentration of the reactants means that the rate will decrease because we have less particles colliding over a period of time. And with the products, we start at 0 products, and as we make products, the concentration of the products increases, so that our rate increases over time as well. Eventually, the rate of consumption of the reactants will equal the rate of production of the products, and now we would be at equilibrium. We have these plateaus here, so at time t we've reached equilibrium. Okay, so this is looking at concentration. If we look at it from the angle of rate, we can see that the rate of reaction for the reactants to the products decreases over time. The rate of reaction for the production of products increases, and going into reactants increases until they reach equal. So here at equilibrium, we can see that once we've reached equilibrium, the concentration of the reactants or the products doesn't change, okay, because we are making product at the same time as we are breaking it down and making reactant. So the concentration will never change over time once we've reached equilibrium. And the same goes for the rate. Once we reach equilibrium, we will be at a horizontal plateau in our graphical representation because there is no change in rate of the forward or the reverse reaction. They're both occurring at the same time, so they will both meet at the same point in the graph. So one way of thinking about dynamic equilibrium is to consider a fish in a stream. If you've got a fish trying to swim upstream, you may have seen it with salmon, they've got to keep moving against that current. So they're constantly working against the current. When they reach the same speed as the current, they will appear to hang in space and be suspended and not be moving at all. Okay, so this is what we mean by it being a dynamic state. Even though there appears for everything to be stopped and it to be still, so with equilibrium there's no visible change to our reaction mixture once equilibrium is reached, there is always something going on even though we can't perceive it at the macro scale. At the atomic scale, those reactions are still occurring. So the concentration of the chemical will remain constant. We won't be able to monitor a change in concentration. The pressure will remain constant if it's gases. Temperature will remain constant because the exothermic reaction will be happening at the same rate as the endothermic reaction, so they will be consuming and using that energy at the same time. But the reaction is incomplete. In the reaction mixture, we will have all substances. We will have some of the reactants, we will have some of the products, and they will all be in that vessel because it's a closed system. So they can't escape, so it's always going to be present. So what that means is we often see questions about colour, because a lot of the reagents, one of the ways we can monitor equilibrium shifts, and we'll do this in a prac ourselves, is to look at colour. So if we look at this here at time A, we can see that what is in this vessel is sort of a pale yellowy brown colour, and this is because the product, in this case the NO2, is dark brown when it forms. But we can see initially we've got a small amount of NO2. As the reaction proceeds, as we produce more NO2, it gets darker. But at no point is it colourless, because as soon as we have some product being formed, it's starting to colour the mixture. And we can determine the amount of product in this case by how dark the reaction mixture gets. Okay, so always think about, if we are at equilibrium, we will have a mixture of both. So it could be lighter in colour or darker in colour, depending on how close we are or how much of the coloured reagent is present. But it will never be at equilibrium, we would never be absent of colour, because there will always be all this species present in our system. Okay, so that's it for defining equilibrium. Okay, and our next one we'll look at how to actually sketch these graphs in a little bit more detail.